So this is my equation number 1. In this case, if I write here current is dq by dt. So if we differentiate dq by dt, so C is a constant, B is a constant, L is a constant. So I'm going to have a dv by dt. So that give me here accelerations, right? So next equation is my Newton laws. We can apply here the Newton law. If we apply here the Newton laws, so my Newton law says that there is a rod, and this rod is carrying a current, right? It's going to be carrying here a current. There is a current, there is a magnetic fields. So I'm going to be have a BIL, right? And what is the direction of BILs? This is the direction of my BIL, and external force F is also applied. So get a accelerations. And what does your Newton say? The Newton simply say that total force give me the accelerations. If you apply total force, so total force F is coming from the external. BIL is coming from the magnetic force equals to MA. But what is the current? Current you get from differentiating the charge. Okay, we don't have a resistance here now. So you don't have a resistance. So you get the charge on the capacitor CV and then differentiate the charge, that will give me the current. This dV by dt is my basically acceleration. So you have B, current is CBLA MA. So this side is acceleration, here is an acceleration. You can take it on the one side, and that will give me the answer here. Acceleration is B square L C, L square also A, right? So I'm getting here the accelerations. Okay. But the next, I think you can find out here speed also. Acceleration is a speed is acceleration to time, because this acceleration is coming out to be here constant. So you can give velocity as a u plus at velocity you can give. Next is asking the charge. The charge, yes, after finding out the velocity, I can put into my charge equation that will give the charge. Okay, everything you can find out. So last option, D option is interesting. The charge on the capacitor will never attain steady state value. Yes, because it's a constant accelerations. Speed is keep on increasing. And charge, see the charge here. So charge is depending upon the speed. Speed is keep on increasing. So my charge is also keep on increasing. So you don't have any steady state. No steady state. So it okay? So after 9, 10th to discuss किया था class में हमने. 11th also we have discussed here. 12th I told you this is a curd, and curd you can replace with the straight wires. So the 13th, in 13th, yes or not?
13th one.
13th one. So regarding the 13th one, remember the rotation chapter, this type of problem we have seen in the rotation chapters. It has a translatory plus rotatory motions. You can turn it into a translatory and rotationary. And in my EMI, I told you rotation and translation you can separate. Completely you can separate the rotation and translations. So if I think it is problems, so what is my, this problem say here, there is a rod, and this what is given here in this case, a thin conducting rod or the length L is moved such that the end B, A is the end B, moves along the x-axis, and the A is moved along the y-axis. A uniform magnetic field is existing here. That's my magnetic field exists here. Magnetic field exists in the region. At some instant, the velocity of the B is given. Okay, so they have given you the velocity of the B, right? If this angle is given, in rotation, you can find out the velocity of the A also. or you can find out the omega here also. Okay, so we can find out here. Now he said that at the instant shown, the speed of angular speed of rod P is. So you can do it here many way this problems. So simple way to be consider here is let me consider the velocity of the A here is something downward. Let's say here's V dash. So criteria is that along the rod component must be here same, right? It must be the same component because the length of rod is not changing. So if I say here this is my theta, so V dash sine theta is equals to my V cos theta. So component if you're going to break, so this cos component must be here same. But not cos component. Along the rod, parallel component must be here same. So got the value of V dash. So V dash here is a V cot theta. Now another thing is if we're going to be considered about this rod. So this rod is going to have a omega. Okay. And if we're going to be consider my omega, let me consider the omega about any point. You can consider the omega about any point, doesn't matter. So I can consider the omega about the A, I can consider omega about the center, I can consider the omega about the end points. So it is your wish, you can take omega anywhere. So let me consider the omega about this bottom point. If I consider here the omega about my bottom points, so what you're getting is, so omega is depends upon, omega will give me, it will give me here simply that this end is moving in a circles. If my end is moving in a circle, so I can think of just a minute. So end is moving in a circles. When we say end is moving in a circles, so it behave as a L as a radius. So I can get here, this is my velocity, and that is a relative velocity that is equals to L omega. Now, if I write my relative velocity of the A, so the relative velocity of the A, that these components are cancelling out, parallel component here is cancel out. So only perpendicular component is this. So perpendicular component of the A minus perpendicular component of the B. So I have this perpendicular component here is a V dash cos theta, which are in opposite direction here. Okay? V dash cos theta and minus V sine theta. Why? Because my V dash sine theta and V cos theta, they are equals. So in the relative velocity, this parallel components are being equals. They don't contribute. So I have a relative velocity, and the relative velocity we have parallel and a perpendiculars. Parallel is 0. Only perpendicular is going to be contributed. In the perpendicular, we have V dash cos theta plus V sine theta. V dash, I already told you what is V dash. V dash here is V cot theta. Okay, so it will overall if we're going to write it here as V by sine theta is going to be my V relative. And this V relative, if you're going to be considered in terms of my omega, just give me here L omega. Overall, I'm getting here the value of omega V by L sine theta. Okay, V by L sine theta. That's my omega value. So first thing is he's asking purely from the rotation chapter. In the rotation chapter, option A is that angular velocity. Theta given, yes, theta given 60 degree. Theta here is given 60 degree. So being 60 degree, I can say it's a 2V by root 3L. So option number 1, right? Option A is correct. Okay. Option B wrong. Next, he's asking here the EMF induced in the rod AB is. So if I'm going to consider the EMF induced in the rod, so you're going to be have the rod is going to be have two effects. One is the omega, and second one is the translations. So can I break into a pure rotation and translations? Yes, we can rotate, we can break it. So I can assume here pure omega. And I can also consider here as the pure translations. So I can consider here as a pure translation. The pure translation means everyone is here is moving with the V, right? So we have a cross, dot. Magnetic field is a dot. It is not cross. So we have magnetic field as a dot. Okay. So if we take it here as a dot, so as a result, my V cross B in the downward direction over here, V cross B. V cross B, yes, V cross B is going to be here in the downward directions. And the components responsible, it's going to be here my theta component is yes. Okay, that is my theta component is yes. So in the V cross B, you can consider the angle. Okay, V cross B, this side is going to be have a positive terminal, this side is going to be have a negative terminal, right? So because of translation, first we can find out the EMF. Translation is give me a V cross B dot L. If you take it here as a V cross B, this angle is 90 degree and dot. If you consider here my dot angle, so dot angle is going to be my angle between the L and the V cross B. That is my 90 minus theta. Okay, basically 30 degree, right? Theta is 60 degree, no? Which comes out to be here my vector L. So it is going to be my 30 degree. So VBL sine theta. So velocity given, B given, and the theta, you know, it is 60 degree, √3/2. And because of my omega, what happens? Because of the omega, we have velocity. Okay, dot magnetic field is there. Velocity is going to be in this directions. So you can say here my V cross B is going to be in the upward direction. So upward positive, downward negative. So because of my rotations, I'm going to be have a half B omega. Okay, radius squares. So it's going to be radius squares, R1 square minus R2 squares. Now when you add up, so you can notice whether because of translation, your bottom point is attaining positive terminals and the top is attaining here negative terminals. And because of my rotations, V cross B is in the upward directions. So both are trying to oppose. Okay, both are trying to oppose. If I'm going to write here my net EMF, so rotation and translations, they have opposite behaviors. Okay, so you can put it here negative sign. So it's a half B omega L square, and translation will give me here BVL sine theta. Omega value we have already find out. What is the omega value? Omega value we have find out, na? That was your V by L sine theta. V by L sine theta, this is L squares. So minus here BV, same L. There's no different L. Same L is yes. Both are same L. BVL sine theta. So I hope so you can simplify here. Theta is our 60 degree. For theta 60 degree, you can simplify. Okay, I hope you understand the point here. So sine, once again, we can check it here once again. Sine, this is my V. And dot, magnetic field is a dot. So if you take it here, V cross B is downward. So my lower terminal is positive because of translation and upper one is negative. But if I say my omega, so here, okay, there is one twist is coming here. I have taken the omega this way. I have taken the omega in this way. And in the diagram, they have given the omega in the reverse way. But the omega coming, okay, omega coming in the way I have taken. Omega given in the question, the diagram is wrong. If you think about the omega in the diagram given is wrong. The direction of omega is not the same way as the direction coming out in the diagrams. So maybe if you take the omega direction according to the diagrams, you will get here plus sign. But omega is not coming in the direction given in the diagrams. Okay? So check the answer here carefully. So omega come in the same direction as we have taken. Okay? Anti-clockwise. Have you understand the point here? Omega, any confusions there regarding omega? So diagram omega will not come. So because I don't know, the answer may be given according to the diagram omega, but that's coming out to be wrong. Next, in the 14th, yes, Arvind.
Hello, good morning, sir.
Good morning.
Sir, 11th question, sir.
11th question, okay. So 11th question, what they have given is the potential difference between the point AB will be. 11th question हमने class में discuss किया था ये. This type of one question we had discussed in the class. Anyway, so just listen here. What is asking here the 11th question is, they are given solenoid, right? So when you consider here the solenoid, and the solenoid we have discussed, if there is a time varying magnetic field, it will create the electric fields, and that's my E star electric field is theirs. And the value of the E star electric field is R by 2 dB by dt inside for the R smallest. And I'm going to be have a R square by 2R dB by dt if you are outside the solenoid. So inside the solenoid, we have different expression, and outside solenoid, you're going to have a different expressions, right? So in this situation, the first part is asking from A to B. Here is a A, here is a B, and here is a C. The angles are also given here as 30 and 60 degree angles. Okay. So first part is asking is the induced potential difference between the point A and B. So when you're taking here this induced electric field, AB is the inside part, and for the inside part, my electric lines of forces are going to be circulate, okay? And they are going to be circulate around the centers. If we're going to consider here circulation around the centers, so how it will go? So they are going to be make a tangent on the circles, right? My electric lines of forces are going to be a tangent and satisfy the Lenz's law. So you have to give according to your Lenz's law. So what is my Lenz's law says? If my internal flux here is increasing, if B is increasing, I just given here increasing. If B is increasing, flux is increasing inward. So my induced flux will be in the outward direction as a dot. So current will be in my clockwise direction. So E stars will coming out to be tangent in a clockwise directions. So on the AB, if you're going to consider here on the AB, so on the AB, it's going to be have a component is this, right? Let me draw here this way once again. On the AB, if I'm going to be considered, it's going to be have a components. The field has a components. That is my E stars is perpendicular to the radius, tangent directions. This angle is given here theta, let's say. This is given here L. So R value is going to be L cos theta, right? And we have to be consider this element in this directions. So this is theta. This angle is also going to be theta. So if you write here my EMF will be E star dl cos theta. For inside part, it is R by 2 dV by dt dl cos theta, right? And what is R cos theta? R cos theta is equal to L by 2 dV by dt is alpha, and you have integral only on the dl's. So dl, the integration go from A to B. A to B. So what is my A to B integral? This is L tan theta, 30 degree. So total length of the AB, this comes out to be as my L tan 30 degree. So that comes out to be the potential difference between the AB. Next is asking the potential difference between the BC.
Sir,
So
second
you
one I
can
will do,
approach
sir.
this, you can do the same way, but function
Yes, sir.
should be, this is going to be the functions. Okay?
We should R square by 2R. Yes, sir.
Bas, okay.
Thank you, sir.
That is our question number 11. Was perfect with the concept but scored less. What to do? Regarding the concept, what do you mean by concept here? Theory, derivations. Derivation and theories are not a concept. Okay. In IT preparation, theory and derivations, they are just the beginning of the concept here. It's not the end of the concept here. Major concept regarding the chapter come from the problem solving. So again, so twist in the problems, how they're going to be mold the concepts. If you understand that twist, then your concept is going to be built up. Okay, IT preparation is not in the clarity, it is in the confusions. First, you have to be see the derivations, then you have to twist. With the twist, it creates confusions. Again, if you understand the confusions, then it becomes clear. So without getting confused, your concept is not going to develop. So you have to be understand the concept after the twist. Concept get clear after the twist. Without twist, it is just a theory, derivations. And theory and derivations are simple steps. Again, they are not going to make a concept. So try to practice on the problems, right? We are discussing here on the problems. Yes, Shiva.
Sir, can you explain the question number 13 again, sir?
What happened in 13? What is the doubt here in the 13?
Sir, I didn't understand how you took the EMF, sir.
How we took the EMF? So EMF, how we took that is already we have discussed. When you have a translation and the rotations, I can divide the rotation and the translation separately. When I divide the translation and rotation separately, you can find out the EMF separately and you can add them. If I consider the effect of translations, so due to my translation, EMF is V cross B dot L. Again, velocity is this side, magnetic field is dot. So V cross B is coming in the downward direction. And this V cross B downward means lower one is positive terminal, upper one is negative terminals. And V cross B, velocity and magnetic fields. Velocity right side, magnetic field outward. So angle is 90 degrees. So cross when you open it is 90 degrees. And when you open this dot, L vector, this is my L vectors. So from negative to positive, that is my L vector. So how much angle it is making here? 90 minus theta. So when you open the dot, it is 90 minus theta. Okay? It will give me here. Normally, we open the dot, it will give me cos theta, it gives sin theta here. Now for rotation, we have that formula half P omega R1 scale minus R2 scales. Okay? So R1 here, 1 point is 0 radius, second one is L radius. And the direction, V cross B direction is outward. So rotation makes positive terminal upward, negative terminal downward. Right? So when you are adding the combined effect, so rotation and translation, if you are adding up, so they are going to have a negative sign. Why negative sign? Because rotation gives upward positive, translation gives upward negative. So opposite polarities are there. That's why they will add up here negative. But there is a one problem. There is one slight problem is that if you see the diagram given in the question, omega is given opposite to our omega. Okay. Omega is given in the diagram is opposite to our omega. but the diagram omega is a long one. Omega comes out to be the sense. If you rotate the rod, suppose rod is going to be moving, this end is moving, so it is going to be rotate this way, no?
Yes, sir.
Anti-clockwise. Okay, if this end is moving this way, so omega rotates anti-clockwise. So omega we have taken as the correct direction of omega.
Yes, I understood.
Okay. Chalo, okay, the 14th one, anyone have a doubt on the 14th? 14, 15, 16, 17, 18. Say all doubts. 14, 15, 16, 17, 18. The class needs again. All doubts. The 14th one here is बहुत basic है. 14 भी बहुत basic है. 15th one. 17, 18. 17, 18 is going to be too easy here. Okay, paragraph we can discuss here. So in the paragraph, what is given here in the paragraph is square loop for the wire with the dimension A, one side of which is parallel to another long straight wire carrying a current at a distance of A. The resistance of the loop is given here. Self-inductance is saying to neglect. Initially, the switch was closed and time equal to 0, it is open. So time equal to 0, the switch is going to be open. So what is the net amount of the charge that will flow through a time equal to 0 through a fixed cross section of the wires? Okay. What is net momentum given to the loop during the switching off? So in this question, what he's saying is there is a current. And in the 2-3 problems, I have find out the flux on the loop because of this current. How to find out here? Integrate. Take a small element and then integrate. Okay. So we have discussed that many times. Take a small element at a distance of x. This is here is my dx. This side is a. So I can write here my flux is equals to magnetic field into this area. So magnetic field because of current wire is mu naught I by 2 pi x, and area here is ADX. Integration is my log x, and limit limit will go from the left side to the right side. They are given, this is given here A. So my limit will go from A to 2A. So this is our magnetic flux. Right? Now next one, he said that there is a switch and the switch is going to be open. The moment switch is going to be open, I1 goes to 0. So this comes out to here my initial flux. Final flux current goes to 0. So flux goes to here 0. The charge flow he's asking here, charge flow. The charge flow is the flux by resistance here. So change of flux by resistance. Okay? So change of flux, you can substitute here, that will give charge flow. Second thing is asking net momentum given to the loop during the switching of the current. Now, net momentum given to the loop he's asking here. So let me consider here the current developed here. So this question has to be done in approximation. Exactly, we can't do this question here. So some approximation need to be done for the second part. What is the approximations? I assume that the current in the wires, this will go to 0 very quickly. That is a assumption we need to be considered. Okay. So let's say at any instance, it is going to be induce the current, and direction of the current is such that it will satisfy my Lenz's law. So current in the wire, it will generate the magnetic field in the downward directions, right? Downward, and this is decreasing. Okay. So my current induced is going to be support the process. It is going to support the magnetic field created by the currents. So induced current is also going to be generate the magnetic field in the downward directions. So we have induced current in the same directions. Now this current will give me a force, right? So we're going to have forces are theirs. So I can think of a force. The current is theirs. So force direction is I cross B. If I consider current is downward here, magnetic field is downward here, but magnetic field inward. So I cross B. So I'm getting the force in this direction here. B2 ILs. And the magnetic force on this direction, opposite direction, is a B1 IL. B1 IL. Now current on this two is the same, but magnetic field near the wire is stronger and this side is weaker. And the force on these two wires are exactly going to be cancelled out. They're exactly cancelled out. So net force, if we write here net force, so net force is equals to B1 IL minus B2 IL. So I need assumptions. What is the assumption, Veda? Assumption I've taken that current flow very quickly. Okay. So time taken is going to be very, very small. So the position of the loop is not going to be changed much. Okay, it's impulsive. Suddenly you're going to be switch off. Suddenly. That is important word here, suddenly. So when you have something done here suddenly, that means your magnetic the loop is not able to move it. Okay, impulsive. So we have magnetic field at the point A is a mu naught I divided by 2 pi A. Current is IL. On the second wires, perpendicular distance become my 2A. That is 2 pi 2A IL. Right? For a momentum change, you can say here net momentum change is equals to my impulse. So it is going to be a force into timing. If you take here this force into timing, so many factor here is common. This factor and this factors. So it will give me here it's going to be here my factor of 4 pi A L. And integration give me here on the charge. So this factor is nothing but a charge, and charge here is nothing but a flux changed by resistance. The flux changed by resistance already we have done in the part 1. So one big assumption we have taken here, once again, I have taken that this loop is not moved. So these gaps are constant. So it is impulsive. Very suddenly the current just switch off. So based on that assumption, we have to solve this problem. Even though this assumption is not given in the questions, but without this assumption, it is not possible to solve. So remember, okay? 17, 18 we have discussed many times. 14 also. There's nothing tough in this 14th. Very easy one, basic one. Okay, beta? So I hope you understand here these papers. So paper was easy, not tough one. And total marks, just a minute here. How many marks are there? Total marks? So total marks miss हो गया, कोई बात नहीं. So it was going to be a good paper, easy paper, not tough papers. Okay. According to the topic, this topic is really tricky and the complicated topic was yes. Based on that, paper was not tough. It was quite easy. So if you are scoring here about 30%, that is well and good. Okay. Okay. 35% you can consider as a cutoff. Take it on the safe side, 35%. So you're getting a 35% marks, you're going to be above the cutoff. If you're getting a less than 35% marks, then you need to be worked a little hard. Okay. So anyone else have a doubt in the paper? Right. So this week we continue our EMI, and this EMI for this week we have circuit part. So last class I have told you the concept of inductance. So this week we continue with that concept of inductance. So quickly let me revise you the concept of inductance. Two types of inductance I told you, self and mutual, right? Self-inductance and mutual inductance. So this week your paper will come from the inductance. Self and mutual inductance. Mutual means between the two. Okay? It can be between the three also. It can be between the four also. But for the two, we have a defined in our syllabus. If you have two circuits, the current in the one generate the flux, and the flux is going to be linked with the second loop. So the flux created by the first current on the second loop, it is proportional to my current in the first loop. Flux on the second depends upon the current of the first. So there is a proportionality constant that's called inductance, mutual inductance, right? So more mutual inductance means the first current has a more impact on the second circuit. More M means first current have impact on the second circuit. More stronger impact is theirs. Same way, I can also find out the current in the second effect on the first circuit. So current in the second effect on the first circuits. So that will give me here reverse mutual inductance, reciprocals. So there is a theorem that says the two mutual inductance are same, whether you see the effect of the first circuit on the second, or you see the effect of second on the first. They are reciprocal and they are equal, right? They're going to have equal mutual inductance. Now this calculation of the mutual inductance is a need here some approximation, exactly not possible. We have discussed some cases how to find the mutual inductance. Then next is a self-inductance. This play important role in our syllabus, self-inductance. Self-inductance here means the current on current create the flux. So the on current create the flux. So this flux is proportional to its own current. Okay, so flux is proportional to my own current, and the proportionality constant is going to be called here as a self-inductance. What is the importance of the inductance is, there is a great importance of the inductance here. Suppose I change the current in my one circuit, so it will affect the second circuit, because in my second circuit, flux depends upon the first current, and flux change is generate here the induced EMF. So flux on the second circuit depends upon the current of my first circuit. So my flux, if my current changes, if my I1 current changes, it will create the EMF in the second circuit. That's a strange concept, and we are going to use it again and again. But not in our syllabus, in your daily life, we are using again and again. So current of the one is going to be affect the EMF for the second ones. So as a result, my EMF is induced into the second one. If the EMF can be induced, current can also be induced, right? So what is a strange thing is going to be happen is you will feel that the current here is going to be transferred to the second loop without the touch. So here we feel that without any contact, current has been transferred. Again, it's going to be have this type of effect. So EMF is generated into the second loop. So it is generated by the change of my current in the first loop, or sometime M can also be changed. So M change can also generate here the EMF, but mostly M is considered to be constants. So only first term is taken as a dominant role played by the current change. So it's going to be have action reaction effects. But what about the self-inductance? EMF induced by self-inductance. So self-inductance can also induce here my EMF. So imagine a loop is there, or in this loop, we have a battery E1. And this battery try to change the current. If the battery try to change the currents, it is change the flux. And when the flux is going to be changed, my Lenz's law say it will oppose. So in the oppositions, it will generate a one more battery. That's my induced battery. One battery is my circuit battery, and second battery is my induced battery. So induced battery is going to be induced. So in my circuit, you're going to be have two types of effects. If you want to change the current, there is going to be oppositions. Okay, it's going to be an oppositions. So it's almost going to be a kind of opposition. It's not necessary that current will not change. Current will change. Okay, current is going to be changed, but it is going to have an opposing effect. The EMF is going to be have opposing effect. And how much opposition is there? The flux created by on current is Li. Okay, and EMF is going to be rate of change of my flux. The flux is Li. So any change happen in the Li is going to be induce my EMF. So it's simply you can say that if L is constant, so EMF develop self-inductance. It is going to be L di by dt. So it means this EMF oppose the change of current. Faraday's law or Lenz's law going to oppose the change of current. Own current. If you want to change your own current, it is also going to be opposed. So circuit oppose its own change in the current. This has a very important role in our circuit. So in this concept here, the self-inductance, the property of self-inductance we can use into the circuit. The way we use resistance property into the circuit as resistors, capacitance property into the circuit as a capacitance. Same way that self-inductance property is also used into the circuit, that is called inductor. So common inductor you may have seen is a simply just wrap the wires. If you just wrap the wires, they just behave as a inductors. Simple coil, normal wires. If you just make it round, it is going to be inductors. Or solenoid is our inductors. Best example as inductor is solenoid. Okay, symbol I told you this symbol. It is symbols. So property is simply is it want to keep the flux constant, and to keep the flux constant, they want the current to be constant. So inductor don't allow easily the change of current. It will always oppose the current change. But it does not mean you can't change the current. You can change the current. It will oppose, but you can change. You can change it. So this concept is similar to your inertia. In mechanics, this word here, inertia, is here. No? In mechanics, we have used the inertia. So it's almost similar to the inertia. What is the inertia say? Inertia says that the body is at rest, it is going to be at rest. If the body is in motion, it is continue to be in motions. If you want to move the stationary body, it will oppose. Okay? It is going to be opposed to change any velocity. If a body is at rest, it tries to be at rest. So what is required? You require some external agent is required. The body itself does not accelerate. Okay? If you leave the body alone, it will never going to be accelerate. So same thing is happen with the inductor. If you leave the inductor, it never allow the change of current. Current is never going to be changed. But some external effect can change the current. But when some external effect try to change, it will oppose. Just like inertia. If you apply the force, so there is a oppositions. Now this opposition does not mean opposite force. This opposition is in terms of inertia. So you're getting a less accelerations. Okay, to get here more accelerations, you have to have a applied here more force. So in that sense, it is going to play the roles. So there is a current flow through the inductor, and if you want to change the inductor, it is going to be opposite, right? So regarding the sign, to understand just the sign I told you, suppose you want to increase here, suppose you want to increase the current, right? Now this current increase is going to be opposed by the inductors. So when it is opposing, it will create here the EMF, and this EMF is create the potential into the circuit. And it's a potential. Polarity is very important to be noted here. So in which direction the polarity it will give? So try to understand this always oppose the increase. So who is increasing this current? Some external batteries try to increase this current. So this induced battery is going to be opposite. Okay. So external try to increase the current. So this induced is going to be opposite. So polarity will be plus minus. Right? So I can say if my current is rising, your potential is falling. Just opposite, you want to decrease the current. If you want to decrease the current, my external battery have opposite sign. Okay. Now this inductor also have opposite sign because it is going to be oppose this external one. Okay. Its purpose is to oppose the externals. Okay. Faraday's law always says, or Lenz's law always say, oppose the cause. Oppose the cause. So who is the cause? So cause of my current change is external battery. So it is going to oppose my external battery. So now polarity is something reverse. This side minus, this side plus. So easy to remember. When current rise, potential fall. When current fall, potential rise. Or you can also think here in a mathematical way. So my EMF potential drop across the inductors. So potential drop across the inductor is same as the EMF of the inductors. And by formula, it is minus LdI by dt. Minus sign is there in the Faraday's law, remember? So this minus sign come from the Faraday's laws. So mathematically, you can understand if di by dt positive, then potential is negative. So here, my negative sign play a role. Okay. In the last whole week, I told you this negative sign of Faraday's law doesn't play any roles. But in the circuit, you can use this negative sign for the polarity. Okay? You can use conceptually also, but mathematically, it is also play negative sign. If di by dt is negative, your V is positive. If di by dt is negative, V is negative. Right? If current rising, potential fall. If current decreasing, potential rise. Say it out, okay? So next I discuss here, so what happens if my inductor and the batteries are going to be connected? That is the one problem we have to discuss, yes? This is important here. Energy is stored in the inductors. Energy is stored in the inductors. So how much is energy stored in the inductors? If my current is going to be flow, there is a magnetic field developed. So this field store energy, right? So how much energy is stored? We can easily understand with that. When a current is flowing, you are moving the charges from high energy to low energy. So there is a loss of energy. And where that loss of energy is going, in the inductor, you are not assuming resistance. Yeah? We are taking the example, Vida. Just wait a minute. We will discuss the problem, it will get clear. So these charges are going from high potential to low potential. So energy is going to be lost. But where that loss is there, is it going into the heat? If resistance there, then it is lost to the heat. But it is not a resistance, it's an inductor. Okay? Okay, in nature, resistance is everywhere. But imagine hypothetical situation that there is no resistance. If there is no resistance, where it will go? It will go into the magnetic fields. So energy loss will go into the magnetic fields. It's not a perfect derivation, just a rough idea it will give you. So loss in the electrical energy go into the magnetic energy. Charge is IDT. Potential here is L I di by dt. So dt here is cancelling out. So what is my energy stored in the inductor? It's a half Li squares. Okay? That is our energy stored in the inductors. Okay, I hope you understand this point, right? So now today we can discuss here ahead how to use the inductor into the circuit and what type of circuits we have. So this is called, basically there are three types of circuits we have. We have LR circuit, we have LC circuit also. Okay, LR is first one you can discuss here as a circuit with inductance. It is better to give here the name circuit with inductance. So whenever there is a inductor and my current is going to be rising, there is a drop. And how much drop is there? L di by dt. If there is a inductor and my current is going to falling, there is a rise. L di by dt. In the inductor, this is an important point is it can give both side polarity. The resistance only give one side polarity. Capacitor give one side polarity. Battery give one side polarity. Inductor can give double side polarity. It could be on the left side positive, or it could be right side on the positive. So this is important one. To understand its polarity, I give you one simple questions. Suppose we have a inductor is there, and we have one capacitor on this side, one resistance we have on this side. So this is going to be have some potential. Let's say here's a 10 volt. This side here is my 20 volt. And this side here is a minus 10 volt is yours. Okay, I can give the name here A, B, and C. So this resistance is this resistance, let's say, is going to be my 2 ohm. Capacitor here is a 10 microfarad, and here is a 5 Henry. Henry, okay, Mr. Henry is the unit of inductor. So Henry is going to be that value. So let's say the current coming through the Henry. The current coming through the Henry is my 1 ampere. Current coming through the Henry is 1 ampere. So charge on the capacitor, let's say, it's going to be my 10 e raised to the power minus t by 10. Not 10, take it here as a 2. That is going to be my 2 coulombs. 2 e raised to the power minus t by 10. 2 nahi. Let's take it here as a 20 only. 20, that's my charge on the capacitors. Right? So that is my pictures. And this is a picture at time equal to 0. So at time equal to 0, that is my pictures. So many questions could be asked here. Many questions could be asked here. The first thing I can ask you here is find the current through the resistance. Find the power dissipated in the resistance, right? Second thing I can ask you that find the current through the capacitors. Okay. Find the current through the capacitors. Find the energy stored in the capacitors. Find the rate of energy stored in the capacitors. Many problems could be asked here. Third thing I can ask here is find the rate of inductor. Here, inductors. The rate of inductor current change. How fastly the current change in the inductors. In the inductor, current given is a 1 amperes, but that is changing. So how fastly the current in the inductor is changing. And the second one is the energy stored in the inductor. and how fastly your inductor energy is changing. So yes. So in this process here, that's my simple circuit is here. One side we have resistance, one side have capacitor, one side have inductors. Resistance change the potential because of collisions. Capacitor give me the potential because of charge storage, and inductor give me the potential because of current oppositions. But in all the cases, they all ultimately give me potential change. And because of this potential change, they satisfy the Kirchhoff law. So one thing which remain valid is a Kirchhoff law. First law of the Kirchhoff is valid, and second law of the Kirchhoff is going to be applicable. So any circuit you consider, Kirchhoff law is going to be remain valid. So in the inductor circuit also, your Kirchhoff law is valid. So you have to be think from the Kirchhoff point of view, right? So first of all is conservations. You have to be applied here my conservations. If we apply here this conservations, so how much current you have through the capacitor branch? So current through the capacitor branch I can give as a dq by dt, right? If I differentiate it, if you just differentiate it, it will give me here the value of current. If I differentiate here, I'm getting the derivative is a 10 e raised to the power minus t by 10 with a negative sign. That is my derivative, right? Or at time equal to 0, its value is a minus 10 at, sorry, not minus 10, 2, sorry. It's a derivative is minus 2 at time equal to 0. That is my current through the capacitors, okay? Minus 2. What is the meaning of minus 2? So meaning of my minus 2 is the charge on the plate is decreasing. Charge, direction of the current is such that it will decrease the charge. Okay? So Q is decreasing. So keeping that thing in the mind, my current should be toward the center O. Direction of the current in my capacitor is toward the O. So it will give me here 2 ampere current, right? If this give me here 1 ampere, this give me here 2 ampere. So how much current is passing through the capacitors? Here it will give me 3 amperes, right? So 3 amperes, 2 ohm resistance, 3 ampere, it is going to drop here my potential 6 volt. This is already 20 volt. C is at 20 volts. So what is the potential of my O? If I am crossing from 20, I am crossing this side. From the C, I am crossing and coming to the O. So your potential is rising or falling. You are going against the current through the resistance potential rise. Okay? So it is going to be 26. So what can I say about the potential at the O? It is 26 is this. Sorry, 26. So next point here is that what is the potential drop across my inductor? Potential drop across the inductors. So here, basically, you can see my potential is increasing. It is not rising. It is not dropping. On the right side, in the direction of current, your potential is rising. When potential is rising, how much potential rising here? It's a 10 volt and 26. 16 volt is the potential rise. So I can say here one thing. Potential is minus L di by dt. And this one here is 16. Inductor is a 5. Inductor is a 5. So I'm getting here di by dt, something around 3.2. At minus 3.2 ampere per second is my di by dt. So that is for our inductor. We can say that current through the inductor is decreasing, not increasing. It's not increasing, it's a decreasing. So minus 3.2. David, I hope you understand, yes? That is the core thing in this chapters. In this chapter, sign play very important role. Little mistake in the sign, it is going to be drastically change the result. So pay attention on the sign. Every sign here is important. Okay, I hope you understand the point. Yes. So if you know the current, you can know the power, energy, you can find out. Okay, so these are the extra topics. The power I know it's I square R, so you can find out the powers. Potential energy I know Q square by 2, so you can find out the potential energy also. If you differentiate potential energy, it will give derivative. Inductor energy is a half Li square. Okay, so these extra points you try to find out yourself. So anyone have a doubt in how to find out the current derivative? Confusing. Okay, so let me take it here slightly once again. So what is given? What is given first? So these are the parameters given to you at time equal to 0. So what is given here? Pay attention. At time equal to 0, it is given. This A has a 10 volt, B has a minus 10 volt, and the C has a 20 volt. And the B potential is extra, not required. Okay, so B you can leave it. Capacitor is given 10 microfarad, resistance given 2 ohm, and the inductor is given here 5. So they given current through the inductor is 1 amperes. Charge on the capacitor is given 20 e raised to the power minus t by 10. Okay, this is the expression given. That is already given. Okay, these are the parameters given. So question here is, you can leave this extra point also, just forget about these extra points. We can just focus on the simple point first. So question here, I can ask here the simple point. Okay, later on you can find out here extra point also. So the simplest thing is find the derivative of current in the inductor. How the current in the inductor is changing, rate of change of current in the inductors. Again, rate of change of current in the inductors. So rate of change of current in the inductor depends upon the potential across the inductors. Okay, so potential, I know what is the potential at the A. I don't know what is the potential at the O. So I want potential here at the O. So this potential you can find out by applying the Kirchhoff laws. Yes or not?
Sir, what is hello?
What is?
Sir, what is di by dt, sir? Like exactly, you know, it is the current passing through the inductor time t.
Current is passing through the inductor. Yes. 1 ampere current is passing through the conductors. Is it going to be remain 1 ampere forever? Or it will change?
It will change.
It can change. Depending upon the circuit, it can change.
So now di by dt means
it
how
may
much
be,
current? How much
di by
current is
dt,
passing through inductor, sir?
di by dt means not current passing through the inductor. Di by dt means how fastly your current is changing. Derivatives means what?
Rate, sir. Yes, sir.
Rate. So it is just rate only. So it is not a 1 ampere. It is not going to remain 1 ampere. This 1 ampere current is going to be changed. Okay? This
Yes,
1
sir.
ampere current is going to be changed. So how much it will change? That is the questions.
Okay, sir.
Okay?
Yes, sir.
That is here my questions. So without twisting here much, simple question I'm asking here. How much is my current changing? If you want, you can further take it at time equal to 0. How much my current is going to be changed at time equal to 0? Option 1. Second option I can consider at time equal to 10 seconds. Second question is time equal to 10 seconds. That is 2 timings. What is my current change through the inductor? So we can analyze here this situations. It satisfies my Kirchhoff law is going to satisfy. So at time equal to 0, if I consider, so charge is on the capacitor is given, and charge on the capacitor is given here as a 20 e raised to the power minus t by 10. So if I write my current through the capacitor at any time instance, what is the current through the capacitor at any time instance? So current means the change in the charge on capacitors. So just differentiate here dq by dt. That gives me the current through the capacitors. And what is the derivative here? We differentiate the exponential functions. Exponential function derivative is exponential into you apply the chain rules minus 1 by 10. So how much is my current? Minus 2 into exponential factors. Right? That is my exponential factor current. Now this minus sign, what is the meaning of this minus sign of the current here? The minus sign of the current means my dq by dt is not increasing. Charge is not increasing. Charge is decreasing. That is the meaning of negative derivative. Now, if you have a negative derivative, means value decreasing. So charge is decreasing. So in the question, I have given you the lower plate positive, and this is decreasing. So decreasing means where the charge going? The charge is moving toward the O, right? It is moving toward the O. At time equal to 0, how much is my current through the capacitors? It is minus 2 e raised to the power 0, timing 0. So that gives me here minus 2 ampere. Okay, so current is going to be 2 amperes. At time equal to 10 seconds, what is the current through the capacitors? It is minus 2 e raised to the power minus 1. So it's a minus 2 by e amperes. So current through the capacitor is minus 2 at the beginning of time. After 10 seconds, what is the current through the capacitor? It's a minus 2 by e. First, understand the minus sign. Minus sign means there is a no current toward the plates. There is a current away from the plates. The plates are losing the charge. So that is my direction of IC current. So in the beginning, this is your 2 amperes. Okay. And 1 ampere current is coming from this side. Now. It's given in the question. In the inductor, it's given that a 1 ampere current is through the inductor is theirs. And the A has a potential of 10 volts. So this is my 1 ampere and 2 amperes. So how much passing through the resistance? Kirchhoff law. Anytime you can find out, any times. So this is 1 ampere, this is 2 amperes at time equal to 0. So this will be here 3 amperes. 3 amperes. So 3 ampere, and this is my resistance of 2 ohm. It's given here resistance of 2 ohms. So when you have a 2 ohm resistance, means it is going to be a 6 volt. Potential is going to be 6 volt. Or in the direction of current, you have a decrease of potential. So it will be plus sign, it will be minus sign. Or C potential is given your 20 volt. So what can I say about the O potentials? C is 20 volt. Okay, if I go toward the O, you are raising the potential to 6 volt. So what is the potential at the O? It will be 26 volt, right? So I got here the potential of the O. This is my 26 volt. Right. So till now we have not discussed about the inductor. We are just use our Kirchhoff law. Now we come to the inductor's property. So what is the inductor property says? Inductor property says that potential is equals to L di by dt with a negative sign in the formula. Now what is the potential drop here? In the direction of current, your potential is increasing or decreasing? On the A it is 10 volts. On the O I'm getting 26 volts. So your potential is increasing. No? So it is a plus 16. L is a 5. So I'm getting here di by dt for the inductor. In the inductors, how much di by dt I'm getting is? It's going to be a 3.2 minus 3.2. We are getting here di by dt in the inductors. So in my inductor, current is decreasing at the rate of 3.2. Right? Is it okay? Clear? This is the picture at time equal to 0. So if I want any other time, okay, any other time, this is my picture at time equal to 0. So it is a transient state. Keep on changing every time. So it is not going to remain permanently the same. Next time, the next time my charge on the capacitor is differ. So current on the capacitors is changing exponentially. So as my current on the capacitor changing exponentially, so everything is going to be changed. The remaining part of the circuit is also going to be changed. So for 10 seconds, my picture is quite different. So for 10 seconds, I can redraw the structures. For 10 seconds, at t is equal to 10 seconds, how is the pictures? So charge on the capacitor is at 20 exponential factor. So current on the capacitor is a minus 2 into exponential factors, or at time equal to 10 seconds, I can say my capacitors is minus 2 by E current. Capacitor current is minus 2 by E current. So it will give me the capacitor current is 2 by E ampere current is there through the capacitors. Through the inductor, how much current is coming? Current coming to the inductor is 1 amperes. Okay? So how much current is passing through the resistance? Current passing through the resistance here is this side is 1 ampere. So the capacitor is coming 2 by E amperes. So through my capacitor it is 1 plus 2 by E ampere current is there. So it'll give me here this potential drop. Okay, so potential drop is this. This side is given here 20. So what is my potential of O? So I can say that potential of O minus potential of C is equal to IR. Current is 1 plus 2 by E. Resistance here is 2. And potential of the C is 20. This is my 20 plus 2 plus 4 by E, 22 plus 4 by E. That is the potential of O. Now at the A, potential is given here as my 10 volts. Okay. At the A, potential given here 10 volts. At the O, my potential is 22 plus 4 by E. So across the inductor, for inductor, if I write here, what is the equation for the inductor here? V is equals to minus L di by dt. Okay. So it is going to be O minus A L di by dt. O potential is 22 plus 4 by E. A potential is 10 volts. L is a 5. So I'm getting here di by dt. That's it. So slightly the mathematics has been changed. Concept is the same. So it is 12 plus 4 by E divided by 5 with a negative sign. So di by dt. That's my current at time equal to 10 seconds. how you assign positive and negative sign for the resistance. That is a very pathetic situation if you don't know how to assign the sign on the resistance. In the direction of current, resistance drop. If there is a resistance and current is going to be flow, so current flow from high potential to low potential in the resistance. Okay, high to low. Current always flow from high to low. So plus to minus for resistance. Oh yes, Sunat.
Sir, in this, after 10 seconds, there will be some current change, no, sir? Even now we are taking 1 ampere only passing through the inductor.
Oh, what you are saying? Okay. You're right. Right. Yeah, this is actually not a properly the questions. You're right. Current is going to be changed through the inductor. You're right. Okay. You're right. Current through the inductor is not going to be changed here. Actually, we have not started here our circuit discussion. Just roughly, I'm just telling you the sign, how to take the sign only. That is only I want to just convey the message. So don't think it as a complete pictures. This question is incomplete. So let's go to the circuit and it will be clear.
Sir, then the current change in current is not constant, means how can we tell that how much current has changed?
You're right. You can take here this pictures. You can think as two different cases. Okay, think of it as two different cases. Case 1 and case 2. Sorry, assuming that current remain here constants.
Okay.
How to deal with the circuit? I'm just going to come here. In this question, I'm not discussing how to solve the circuit. I'm just discussing how to take a polarity. Okay.
Okay, sir.
All कुछ भी नहीं था इसमें, ठीक है? So it's not in that sense.
Okay.
What happen if capacitor is going to be placed? I'm coming to this topic. Okay, this topic is not started. Okay, till now topic is not started. Don't think that topic is over. It is not started. This question is discussed to only take the sign of the inductors. How to take the sign of inductor? That's it. Right? Just understand how to take the sign of the inductors. Nothing more than that. So we are discussing here about our circuit with the inductors. Okay. So I hope you understand here the sign of the inductors. So to make it here a little more clear, I take here one more case, simpler one. If you're getting confused, we can take here one simple situations to get here clearly the sign of the inductors. Let's say we have a resistance. Here is my, let's say, 2 volt, and this side I'm going to be have a, let's say, 5 volt. This is my 2 ohm resistance, and here is a 10 Henry. Okay, that's my 10 Henry is there, and the current is going to be passing here as a, let's say, 3 amperes. Just only to get here the polarities. Okay, to get the clear about the pictures, polarity pictures. Only focus on this polarity point first. These points are A, B, and here is a C. Right? So can you tell me how fastly the current is changing in this circuit? Current is increasing or decreasing? Current, the 3 ampere is increasing, or the 3 ampere here is decreasing. So what is happening to the current in this branch? So if you just pay here, so how fastly the current changing in the circuit, that is decided by inductor, not decided by the resistance here. Okay? So resistance, we know that for resistance, it's a simple idea is that Ohm's law, V is equal to IR. Ohm's law will only follow. So V is equal to IR. We have a current of 3 ampere, resistance of 2. So I can say it is going to be have a 6 volt. And which side is the plus and which side is the minus? For resistance, we have simple sign. Current always flow from high potential to low potentials. Okay? I hope so. No one have confusion now. For resistance, there is simple sign. High potential to low potential current flow. So this will be a IR. Potential is IR. I3 resistance to 6 volt. So what can I say about my C potentials? If I'm crossing the resistance, it will increase the potential 6 volt toward the C. I will decrease the potential 6 volt toward the B if you're moving toward the B. So C potential, I can say 11 volt. Clear? C potential is 11 volt. Now for the inductor, now you have this is a 2 volt and 11 volts. There is a drop of 9 volt. So we have a 9 volt and keeping this side positive, this side negative. If I'm moving this side, your potential is decreasing. This side, your potential is increasing 9 volt. So for my inductor, I can say potential is equals to minus L di by dt. So how much potential has been changed? Is it a positive change or it's a negative change? So you are going in the direction of current. So your potential is rising. So it is considered here as a plus 9 for the inductors. In a formula, we have minus sign. Inductor here is a 10 volt. So di by dt is coming out to be 0.9 negative. So means current is decreasing. Okay? Right? Clear? Current here is decreasing. We are discussing inductor circuit. Yes, Satish.
Sir, once say how did you get positive and negative?
How we get here the positive and negative.
Yes, sir.
So for positive and negative for resistance. For
That one
resistance,
I didn't
my
understand, sir.
for resistance, it's simply in the direction of current, your potential always drops. Okay, so in resistance, there is no confusion.
Yes, sir.
In the inductor, you have both the possibility. It can rise or it can fall. Okay, both the way it can behave. Up to now, we have discussed resistance, capacitor, battery. So resistance, capacitor, battery, they have single sign, either positive or negative. They don't have a double sign. But inductor can play both the signs. That's why its a role should be understood here clearly. So when I through the resistance, I know it's a 6 volt potential is there. 6 volt potential drop is there. So this is 5 volt. You cross it, it gives me a 6 volt, 11 volt here. So at the C, I'm getting here 11 volt. A potential is given 2 volt. C potential is 11 volt. We calculate it. So if you're crossing from A to C, you have to increase the potential 9 volt. You know?
Yes,
So this
sir.
side is positive. This is low potential. This is high potential, right?
Yes, sir.
This side is low potential. This side high potential. So through the inductor, if you are crossing in the direction of current, your potential is increasing. So
Sir,
my
by the
potential is plus
by the
9.
potential we used to give sign, sir.
What?
By saying a potential, we have to give sign, sir.
Repeat again.
Hello, sir.
Repeat again. Satish, your potential is going to be in the direction of your current. Okay? In the direction of current, you're rising or falling. Okay? So potential is minus L di by dt. Formula is minus L di by dt. So here it gives me potential is a plus 9. Inductor is given your 10. So I'm getting here di by dt as a 0.9 negative. So current is decreasing. Okay? Current here is decreasing. right? So I hope you understand here the sign of this inductor. So if you understand the sign of the inductors, we can start our circuit. So there are two major types of circuit we have with the inductors. One is a LR circuit and one is a LC circuit. Again, two important circuits are there. Can we consider motor as the inductor? No, solenoid is inductor. Any wire which has a wire coil, wire wrap is going to be have an inductor. So inside the matter also you have a coil. So it has a inductor properties. Just like any wire has resistance, so any wire has an inductor property also. Okay. So listen the topic here. So one simplest circuit we're going to have is a LR circuit. This is the most simplest type of circuit is this, because resistance is present in every wires, collision is happening everywhere, so resistance is there. Inductor is going to be the property of our natures. Every circuit has a property to oppose the current change. So inductor is also present in every wires. So inductor and resistance, these are the two property which are present in every wires. So LR circuit is going to be a very important circuit in our natures. Okay? So symbolically, we are going to represent here L and R circuits. So two types of L and R circuits we have. It's going to be called here as a growth circuit, and the second one is a decay circuit. So growth circuit first we can discuss here as growth circuit here. Growth circuit means your current is growing. That's called here growth circuit. So the circuit is made up of L, R, and a battery. That is a simplest growth circuit is this. Now you can see that it is like a RC circuit. Look like RC circuit, no, or not? It is looking like a RC circuit, and its property is also like a RC circuit. So a lot of features are same as my RC circuit is this. This circuit is going to be called here as a growth circuit because battery is going to establish the current. Okay. So if I say that at time equal to 0, switch is closed, then what will happen? So all these three elements behave according to their character. Battery character is to push the charges, so battery is going to be push. Okay. Resistance character is to have collisions, and through the collision it is going to be get some potential drop. So resistance is going to be collide and decrease the potentials. Inductor nature is to oppose the flux change, or in this process of flux change, it will drop the potentials. So all these three elements has a different character, but one thing is common. Inductor, resistor, and battery all drop potential. Reason may be different, but all drop potentials, right? So they have different reasons, but they have a common potentials. So I can say that at any instant, let's say this battery is pushing, my battery is pushing the charges, and at any instant, the battery has been created the current. So this current is going to be flow into the circuit. So if current is going to flow, it will drop the potential across the resistance. A battery, when push the charges, it is increase the energy of the charges by E potentials. Now inductor is also going to be dropped. They are going to drop the potential if current is